Good afternoon and happy post-Hanukkah celebration. So now we have to in the last lecture 2 weeks ago we were speaking about perturbation theory, which is part of global analysis. So in global analysis we have a small parameter epsilon that we put somewhere in the equation. Then we write y of x as a sum of epsilon to the power of n y n of x, and calculate from n equals 0 to infinity or whatever, and calculate things order by order in epsilon. So it's not like in local analysis, taking the distance from x to x naught as a small parameter. Instead, we are taking epsilon to be the small parameter. Which is epsilon, yes, okay. Now, we made a distinction between anomalous singular perturbation theory and regular perturbation theory. In regular perturbation theory, when we take epsilon to 0, as epsilon go to become smaller and smaller, we get the solution of the equation without the epsilon. In singular perturbation theory, we cannot do that. For example, if you remember this trick with something like epsilon x to the 4 plus x squared plus 2 plus 4 equals 0 or something, I don't know. So when epsilon goes to 0, when epsilon goes to 0, we lose a few solutions, and these solutions were going to infinity. So there is no simple convergence of the, or at least of some of the solutions of the equations to their value at epsilon goes to 0. Okay? Now, today we are going to present another very important type of singular perturbation theory that is more complicated than this one, but it's very important because there is also a way to analyze it called a boundary layer. So for the moment today we are going to speak about boundary layer theory. Okay. And to emphasize, or to as an introduction for the boundary layer theory, let's consider a solvable case. But I want to, because it's solvable, it may help us in order to explain what is going on here, right? So let me consider the following equation. I have epsilon y double prime plus 1 plus epsilon y prime plus y equals 0 with a boundary condition y of 0 is 0 and y of 1 say is 1. I think so. Yeah. Okay. You see? Now, why this is a solvable case? Because, as you know, this is an equation with constant variables. So we know that the solution is a constant coefficient. So we know that the solution must take the form y goes like e to the alpha x. We only have to find alpha. And if we plug it here, then first derivative is just like taking alpha out. Second derivative is like taking alpha squared out. And then the exponent cancels because it's a homogeneous linear equation with constant coefficients. So we find that epsilon alpha squared plus 1 plus epsilon alpha plus 1 equals 0. This is a characteristic equation for the alpha. Do you understand that? Yes. If you miss it, then you miss the rest of the lecture. So Just make sure that you understand that. Right? Any problems with that? Good. So now we have to solve it. We have a quadratic equation for alpha. So I can write that alpha is what? First of all, I have to divide, so I have 1 plus epsilon divided by 2 epsilon with a minus sign. And now I have plus minus, again, I have 2 epsilon here. And here I have the square root of 1 plus epsilon squared minus 4 epsilon. Now, the trick was, just in order to make things easy, that 1 plus epsilon squared minus 4 epsilon is what?
1 minus
Is 1 minus epsilon squared. Right? So I will have minus 1 plus epsilon divided by 2 epsilon plus minus 1 minus epsilon divided by 2 epsilon. Okay? So what are the possibilities? If I'm taking the plus, there are two roots. If I'm taking the plus, then I have 1 plus epsilon plus, I have minus 1 minus epsilon plus 1 minus epsilon. So I get minus 2 epsilon. And minus 2 epsilon divided by 2 epsilon is minus 1. What is the other root? I have minus 1 minus epsilon minus 1 plus epsilon. Epsilon cancels out, and I have 2. So I have minus 2 divided by 2 epsilon, so I have minus 1 over epsilon. These are the two roots of this equation. Okay? Which implies that the general solution of this equation is y equals to a e to the minus x plus b e to the minus x over epsilon. Right? This is e to the minus alpha x, where alpha is either minus 1 or e to the alpha x, or when alpha is either minus 1 or minus 1 over epsilon. Okay, how do I decide what a and b are? The boundary conditions. What are the boundary conditions? So first of all, I want y of 0 to be 0. This implies that when I put here x equals 0, I'm getting a plus b, it must be 0. So b must be minus a. Right? And then I have to make sure that at 1 is 1. So I will leave you to convince yourself that the solution is e to the minus x minus e to the minus x over epsilon. This is like saying that b is minus a. Right? And then a should be defined such in a way that when x equals 1, you will get 1. And this is the way. Right? So please convince yourself that when x goes to 0, this is 0. When x goes to 1, the denominator and the numerator are the same, so I will get 1. Okay, so this is a solvable equation with this solution that I will mark in purple. Okay? Good. Now, so let's plot it. So now this is x, and this is 0 of course, and this is x equals 1. Right? We know what we know. We know that when x equals 1, y is 1. We know that when x equals 0, y is 0. Now, what will happen when epsilon, what will happen if we take epsilon to 0? Let's assume that epsilon is very, very, very small. So as a first approximation, I'm taking epsilon to be 0. What does that mean? If epsilon goes to 0, what is e to the minus 1 over epsilon? 0. What is e to the minus x over epsilon? 0. Okay? So if epsilon goes to 0, as epsilon goes to 0, apparently I can say that y is e to the 1 minus x. Okay?
Minus x plus 1.
What?
E and the numerate.
E to the minus x over e. Wait. You're right.
Minus x plus 1.
Sorry.
That's the same thing.
E to the minus x over 1 over e. Right? That's e to the minus x. That's e to the minus 1 minus e to the 1 minus x. Okay? So, how this function looks like. First of all, at x equals 1, how much is that? 1. So it satisfies the right boundary condition, but what's the problem?
That's 0.
It does not satisfy the left boundary condition, because to the left we have e to the 1 instead of 0. So this y is actually starting at e and going down to 1. This is a solution that I will get if I will take epsilon to 0 here. Okay? So you see what's happened. It does not converge to the correct solution. Why? Because the correct solution must end up here, not here. So what's going on?
Can you explain again why the correct solution is?
The boundary conditions are my choice, right? Or the choice of Bender and Orsag, right? And we have chosen these boundary conditions. These boundary conditions tells us that when x is 0, y is 0.
Okay.
Say it another way, if you want to feel better what gets wrong here, when I'm taking epsilon to 0, strictly to 0, the equation is becoming first order instead of second order. And of course, for equation for first order, you cannot enforce two boundary conditions. You have only one boundary condition, right? So this is what's happened here. We took epsilon to 0, and instead of getting something that ended up here, we find something that ended up here. That's a problem, okay? Now, however, what's happened, so this solution is fine, right? This solution is fine, it satisfies both boundary conditions and everything is good. Why this solution do not converge to this solution when epsilon is small?
Because x equal to 0 is spatial case.
Exactly. Because no matter how small is epsilon, so suppose epsilon is 10 to the minus 6, okay? There is still region. What I said is that this and that are negligible when epsilon is going to 0. This is wrong, because no matter how small epsilon is, like epsilon 10 to the minus 6, I can still take x to be 10 to the minus 8, and it will be large. You see? So if you plot this solution and take epsilon to be smaller and smaller, you will find that it is doing something like that. Okay, it goes here and then goes to here. This is for, say, epsilon 0.1. Now, if epsilon is 0.01, it goes here and then goes here. No matter how small is epsilon, right, you are going to have a region here where the behavior of the system is of the solution is dominated by the ratio between x and epsilon, right? So for every small epsilon, there is an even smaller x in which the solution is making such a turn, and this is and this is the boundary layer. So if epsilon is very small, the smaller is epsilon, the thinner is this boundary layer, right? But the point is that it's singular perturbation theory because it never converges to this region. Okay. So far, in some sense, I explained what the problem is, right? The problem is that I cannot take epsilon to 0 like here because I will get the wrong solution. And I cannot take epsilon to 0 here. Okay? So you can say, what's the problem? You should work with this solution. This is the exact solution of the equation. Yes? But the question is, what I should do when, this was a very simple problem. It's a problem of homogeneous equation with constant coefficients, which is linear, right? Then yes, then write down the solution and stop thinking about that. But if you have an unsolvable question, right, because the coefficients are not constant, and so on and so forth, then you want to know what to do, because you cannot find the solution, you want to use an approximation. And you want to implement the fact that epsilon is small, but you know that you cannot implement it here. That's the problem, right? Given that epsilon is small, is indeed small, right? If epsilon is large, then it's not a story. If epsilon is indeed the small parameter in the problem, then you have then you know that you have some, and epsilon is the coefficient of the highest derivative, right? Then you know that you are going to have a region where the taking epsilon to 0 will not give you anything. So the question is how to get the benefit from epsilon being small without killing the solution, right? So suppose I don't know to write that. What should I do in order to get the benefit from epsilon without, from the knowledge that epsilon is small, but still being able to fulfill, for example, both the boundary conditions? Do you understand the problem? Good. So, so let's start thinking about this problem. Now, suppose that I don't know, they forget to teach me that that this is a solution. I don't know how to solve equations in constant coefficients, right? I want to arrive to a solution based on the fact that epsilon is small. But since I have a boundary layer, I should be able, I should do something, right? So the trick is, now I will demonstrate it for this problem, which is again solvable, and there is no point in doing what I'm doing now, but this is a demonstration of a method. Okay? So the trick is, I want to divide things into two regions, y in and y out, where out is here and in is a boundary layer, right? Just give me some credit. This is what I'm going to try to do. So let's try with y out. For y out, you agree with me, and of course you can argue about why I've chosen this to be out and this to be in. Maybe this is in, this is out. We will arrive at all these problems later. But for the moment, for y out, I can simply say, very simple, epsilon is 0. So for y out, I will get y out prime plus y out equal 0. You see? No problems? Okay, so again, I can plug the e to the alpha y is e to the alpha x, right? The ansatz, the general ansatz, because this is also a linear equation, a homogeneous linear equation without a homogeneous linear equation in constant coefficients. So I find that alpha is equals, alpha plus 1 is 0. So alpha is minus 1, and therefore y out is some a e to the minus x. Okay? Now, which boundary condition is irrelevant?
The one.
The right one, right? Because the left one is in the realm of y in, right? We are not talking to the left one. We are talking to the right one, okay? So we got this, y out is a to the minus x, and now we want y out of 1 to be 1, and therefore I will say that a must be e, right? Because e to the minus 1 is 1, so I will got that y out is e to the 1 minus x, which is exactly what we found. Okay? So this is the outer solution. Fine. Now the problem is what happens inside. What is the inner solution? Okay? So what will be the solution in this region? Of course, we cannot take epsilon to 0, but now we understand why we cannot take epsilon to 0.
Because x is smaller.
Because x is very, very small. Okay. So x is actually, when I am in the inner region, when x is much smaller than epsilon. Okay? So we have two small parameters in the problem. One of them is epsilon, and another is x, which is even smaller than epsilon. Okay? So what I should do? The trick here, we will elaborate on this trick later on, but for the moment, the trick is I would like to write the same equation, but in terms of x tilde, which is x over epsilon. Right? So when x is much smaller than epsilon, x over epsilon is still order 1. If I will write the equation using this parameter, I will have only one small parameter in the problem, which is x, which is epsilon. You see? Okay? Good. So if x tilde is x over epsilon, then I should use the d dx is d dx tilde, dx tilde dx tilde dx. But what dx tilde dx is? 1 over epsilon. And correspondingly, d2 dx squared is 1 over epsilon squared d2 dx tilde squared. Just the chain rule. Okay? So, if this is the case, now let's write the equation again. We have epsilon divided by epsilon squared times y double prime. Now, this prime is prime with respect to x tilde, not to x. Very important. Right? You see what I mean?
Yes. Yeah.
Don't miss it, because then, yes, this is now a second derivative with respect to x tilde. Again, plus 1 plus epsilon divided by epsilon y prime, again with respect to x tilde, plus y equals 0.
Maybe you can do y dot instead of y tilde.
Maybe just the
I'm afraid that if I will do that, it will be more, because then you think about time,
Wait, but what about
right?
d over dx tilde?
Because I have to write these similar equations 10 times during this lecture, and they will get complicated. You want me to somehow, okay. Is that better? Such y is a function of x tilde.
Okay.
Okay.
I'm afraid that I will not survive. But anyhow, okay. Y is a function of x tilde. Okay. And now you see that this cancels with that. And we can multiply everything by epsilon now to obtain y double prime plus y prime plus epsilon y prime plus epsilon y equals 0. I just took this equation and multiplied by epsilon. Now you see that the highest derivative have no epsilon in front of it. Right? It's the same trick, if you remember, that I did with the algebraic equations. Right? To get the asymptotic behavior. So now I want the asymptotic behavior close to 0, and I have this, and because of that, now I will neglect epsilon. Right? So to neglect epsilon is to neglect this part, and what I will find is y double prime plus y prime equals 0. How to solve this equation? Again, the answer is e to the alpha x. So I have alpha squared plus alpha equals 0. So I have two solutions. One of them is alpha equals 0, and the other one is alpha equals minus 1. Therefore, y is, so y, right? When it's in, it's this y, when it's out, is that y, right? So y is what? Is some constant, let's call it b, e to the minus x tilde plus c. See? Okay. So we have two constants to decide about, but we have a boundary condition. What's the relevant boundary condition?
The 0.
It's the 0. So I want when x goes to 0, when x goes to 0, x tilde is also 0. Because, yes, no matter how small epsilon is, when x goes to 0, x tilde is also 0. So we want b plus c to be 0, which implies that c is minus b. So what we have here is actually b times e to the minus x tilde minus 1. That's a solution of in the inner regime, right? So the outer solution.
And the free parameter is to connect the two solutions.
Wait. I should wave hands a little bit. Right? The outer solution is e to the 1 minus x. Because in the outer solution, we drop the second derivative, we have only one constant. And we decide this constant with the right boundary condition. Okay? In the left solution, we have a second derivative here. So we have two constants. One of them was determined by the left boundary condition, and we were left with one constant. So now the question is, I solved it here, I solved it here. The question is, what is b? Okay? So in order to decide what is the value of b, right? Okay? What we do is a technique called asymptotic matching. Asymptotic matching means that I want this to match this, right? When?
It's 0.
Okay, when?
At the boundary.
The question is,
the difference between them.
okay, you see, at least in the figures, and you can plot, right, the exact solution, you see that you have this solution that more or less satisfies that, but it matches this solution.
X tilde goes to x.
What?
הנגזרות שווה 0 ואז זה.
No, okay. So
maximum.
you are all familiar with a technique used in the solution of piecewise continuous potentials, right? When we have a potential well like that, and what you are doing there is patching, litfor, right? You patch by making psi equal psi of 0 from the left up to the right are the same, and psi prime, right?
Someone said in the back, and the minus between them is going to 0.
this, okay, now what we are doing is not patching, but matching. It's a different concept, right? Don't mix between the two. Asymptotic matching is based on the following idea. First of all, what was the assumption that was required? Let me say like this. The idea is I will find a region where both approximations are correct. Right? You see, I did two approximations. Right? One of them was based on the idea that x, right? Here, the approximation was based on the idea that x is much larger than epsilon. Epsilon is negligible with respect to x. Right? This was the story here. What we assumed here is that
The other way around.
what we assumed here is that x,
Epsilon is not zero.
here we assume that x is much larger than epsilon, okay? But I can add another assumption that does not violate it, but that will not violate this assumption. And the assumption is that now let's add another assumption, which is x much larger than 1. This and this will not violate each other if at epsilon goes to 0. So if epsilon is 10 to the minus 6, I can take x to be 10 to the minus 3. On the one hand, it is much larger than epsilon. On the other hand, it is much smaller than epsilon. On the other hand, it's much larger than 1. Right? So the black condition do not violate the blue condition. You see? This is a condition for y out. And this is another condition that may live happily with that condition.
Shouldn't be x smaller than 1?
Sorry. Right? We can happily assume that 10 to the minus 6 is epsilon, say, and x is 10 to the minus 3, say, and 1 is 1. So x is much smaller than 1, still it's much bigger than epsilon. Right? So there is a region where I can assume that both these conditions hold. Not only that, this region is growing and growing as epsilon goes to 0. Right? No matter, at some place, it will be, if I will take epsilon to be smaller and smaller and smaller, the ability to find such a thing is becoming even better and better and better. Right? So if epsilon is 10 to the minus 8, then I can say x is 10 to the minus 4 and 1 is 1. Right? So, right? And in this region, what will be y out? E, right? E. Okay? Now, what's going on here? Here, I will add another assumption, which is that x tilde goes to infinity. Right? This is, so here, the basic assumption was, okay, we have y in and we have y out, right? So we derived y out by assuming that x is much larger than epsilon. We derived y in by assuming that x that what is the assumption here? Wait.
Epsilon is not 0.
That we derived this by assuming, I had it in mind a second ago. Okay.
Isn't it supposed that x over epsilon is for 1?
I will recover it during, while speaking, I hope. and we added, I mixed the colors, but anyhow, we added an assumption that x is much smaller than 1. And there is no contradiction between the two, right? Here I would like to add the assumption that x tilde is much larger than 1, right? Oh, okay, I assume that epsilon, yes, okay. This is the assumption I would like to add.
Why?
What?
You assume that x over tilde is very small. How it's
No, okay. I took x tilde, right, to be x over epsilon.
okay?
Okay? Then I did this manipulation, and I arrived at this. So I neglected this. If I do not neglect this, I should get the same solution.
Because you say that epsilon goes to 0.
Yes.
Before you put epsilon go to 0.
So yes, but for every so epsilon is small, right? I assume that epsilon is small, but by the same token I can still assume that x tilde is much larger than 1, right? And if x tilde is much so there is a region here, right? On this line between 0 and 1, I can find a region where on the one hand x is much smaller than 1, so that I can use this approximation, and on the other hand x tilde is going to infinity, again at the same place, right? There is a region, a finite region. It's not a point, it's not patching, it's matching, right? There is a region where this approximation with respect to y out and this approximation with respect to y in should hold together. And in this overlap region, I can say that here I found out that y out is E, and here I will find that y in is what? Is minus b, right? Is minus b. Therefore, patching means that b is minus e. Okay? So, at the end of the day, I will decide that y in is e to the 1 minus x, and y out is e times e say minus, because this is minus e, so I'm putting here minus e, so I will get e minus e to the 1 minus x tilde. You see? Now what is that? This is, if you want, e minus e to the minus x over epsilon. After doing all these tricks, I can return to the original definition of x tilde, and you see that this satisfies the right boundary condition, right? So, this is y out, and this is y in, of course. This satisfies, so y out of 1 is 1, and y in of 0 is 0, right? Because it's e minus e, and it wait. What I did here? It's 1 minus. You should correct my right. So when x equals 0, I have e minus e. Yes. Okay. Yes. So y in of 0 is 0, y out, and both of them match each other in the overlap region. Now you have to plot it in order to see that y in will look like, okay, it's too high. Let's see. you have to plot it in order to see how it looks like, and you will see that, okay, y out is clearly this one, right? Okay, now y in is e times 1 minus z. It will go like it will go like that, something like that. And there is this matching region where both of them overlap with each other. Okay? Now, some people like to write what they call uniform approximation. So now we have an approximation that works here and an approximation that works here. Right? This one it's nice here, but then it gets wrong in this region. And the y in is nice here, and then it gets wrong in the other region. Now, some people like to write a uniform approximation. And the uniform approximation, the way they do that, so the uniform approximation, here, okay? So the y uniform is defined as y in plus y out minus y overlap. So in our case, it will be y in is here they are. So we have y out. Y out is e to the 1 minus x plus e minus e to the 1 minus x over epsilon. You see? But now I have to subtract the overlap. The overlap here is a constant, is e. Right? The value of both functions in the overlap region is e. Right? So I have to subtract e. And you see that the e and the e cancels out. And the uniform approximation is e to the 1 minus x minus e to the 1 minus x over epsilon. Right? To be compared with the exact solution. Okay? How this is doing with respect to the exact solution? You can see that what you can see that, for example, what happens when x goes to 0? When x goes to 1. Sorry, when x goes to 0. When x goes to 0, I have e minus e, it's 0. So the uniform solution satisfies the inner boundary condition. However, the uniform solution do not satisfy the outer boundary condition, right? Because if I'm taking a x to be 1, I have here e to the 1 minus 1 is 1, minus e to the 1 minus x over epsilon. When x is 1, I have e to the power of 1 minus
1 over 8.
So e to the minus 1 over epsilon. Right? When epsilon goes to 0, this term is negligible. You see? And we get the correct boundary. So there is a mismatch, a little mismatch between the uniform solution and the exact solution. Okay? Good. So this is what I have to say. Okay. Yes. Yes.
So we can't calculate y overlap? We can't calculate y overlap?
What does it mean we can't? Here it is. This is overlap.
Okay.
The other overlap function is a good, nice approximation.
For the
It
region.
misses slightly at but the inaccuracy in the overlap goes to 0 as epsilon goes to 0.
Oh.
Okay? If you plot this versus that, right, and again you do it for
Yeah, I'm doing
different values of epsilon, what?
I'm doing it right now.
You're doing it
Yeah.
right now.
If-
And
You want you can probably do it on the PC if you want. You can
Hmm?
show us. You could probably do it on the computer if you want. It will show us on the screen.
where do I have computer here?
אין שם מחשב לבד? צריך לפטופ.
Yeah, I have to.
אוקיי. No, never mind.
In any case, okay. So let me try to summarize the prescription. Right? The prescription is step 1: divide your region into an inner and outer. Solve the problem in the outer, where you usually have only one boundary condition and its complete solution. Solve it in the inner after this transformation, right? And then you have a solution in the inner with two constants. One of them is decided by the left boundary condition. The other one is decided by the matching. Right? Questions so far? Yes.
But all you've got is a long way to say that the second E in the dominator is negligible.
What?
If you're looking on the Y, the exact Y, what you say is the exact
Yes.
solution. All you got the Y uniform is
That this is negligible. Yes, this is negligible. If epsilon goes to 0, this is negligible no matter what x is. Right? So if you and if you drop that, you get it.
okay.
Very good. Good point. Okay. So. Okay. Now I would like to emphasize now that this is. By the way. Okay. Wow. I'm very slow. I would like to emphasize that this is not a. What I would like to emphasize? I would like to emphasize something. Okay. So what I would like to emphasize is that this is not one. I mean that you can implement. You can build a complete perturbative expansion, right? What I did here is the first order expansion, right? So essentially, I can do like that. Right? Yeah. So this was my original equation, but now I can make the manipulations. So I have, let's speak about y out, right? So y out satisfies this equation. Okay. Okay. Let's speak about this as y out. You remember, for y out, epsilon was a small parameter. Okay? And where x is order 1 and epsilon is a small parameter. Okay? So now I can simply write it as y double prime plus y prime plus epsilon y prime plus y equals 0. Right? But I have only one boundary condition that y of 1 is 1. Okay, sorry, and I have, yes, plus, what's going on? No. I have y prime plus y plus epsilon y double prime plus epsilon y prime equals 0. Just copy this with putting the terms that are proportional to epsilon to the right. Okay? So now I assume that y out is a sum from n equals 0 to infinity of epsilon to the power of n, yn of x. Well, again, this yn is yn out. That's why I'm using this, I'm not writing out because it will be too, right? So, and I can now analyze it order by order. Okay? So what I will say to order epsilon to the 0, if I am collecting only, right? I'm plugging this here, and here. Okay? So to order epsilon to the 0, what I have simply y0 prime plus y prime is 0. Sorry. Okay, let me write to make it clear. I'm just trying to clarify things. Let me write it. So I'm taking this equation and I will write. I'm writing it to first order. So I have y0 plus y1 plus epsilon y1. So these are the first two terms here, right? And I plug it here. I have y0 plus epsilon y1 prime plus y0 plus epsilon y1 plus epsilon y0 plus epsilon y1 double prime plus epsilon y0 plus epsilon y1 prime equals 0. Yes? I just plug here the first two terms. Okay? And now I start collecting, I start solving the equation order by order in epsilon. So to the first order, to the zeroth order in epsilon, what I have from here?
Just the one we did for y out.
Y naught prime plus y naught equals 0, right? And remember we have the boundary condition, right? And the way I will solve it, as I remind you last time, where I put the boundary condition, in what orders of the perturbation theory? Only at the zeroth order, and all the other orders, right? So I will replace this by y0 of 1 is 1 and yn larger than 0 of 1 is 0, right? I'm putting always the boundary conditions at the first or as the leading order in the perturbation theory. Yes.
This is also for the boundary condition of y equals 0.
This is
For x equals 0. x0 is 0.
wait. We will go to the left boundary condition immediately.
Okay.
Right? So I just collect terms. So this plus the boundary condition implies that y0 is e to the 1 minus x. This is exactly what we already did. Okay? Now, what's happened with to first order in epsilon?
y1 prime
Isn't it what we just did?
y1 prime
plus y1
plus y1
plus y naught
plus
prime
y naught double prime, right? Plus
y naught prime
y naught prime equals 0, y1 of 1 is 0. Right?
so the first
But we already solved for y naught. We know what y naught is.
and the
is-
first two terms
This is y naught, e to the 1 minus x. So what is y naught prime? Y naught prime is minus e to the 1 minus x. Do you agree with me? And what is y naught double prime?
is y naught e
Just
to the
y naught.
minus
Plus e to the 1 minus x.
Mhm.
Right? So this together is 0. Okay? So this cancels that. Okay? And we find that y1 prime plus y1 equals 0. So y1 must take the so y1 must take, because of that, y1 must be some a e to the minus x. But I want y1 of 1 to be 0. What does it mean?
A0.
A0. Right? No other way. So actually, there is no correction, no first order correction. Okay? And I leave you to convince yourself that this will return. Now if we are going to do y2, right? So we will have y 2 prime plus y2 is equal to y double prime, but y1 is 0, so this is 0, so we have no contribution. So what we found from the zeroth order in epsilon is true for any order in perturbation theory. Right? It's true to infinite order in perturbation theory. The reason why this is an easy problem because it is solvable, but yes.
That's okay. So that's specifically for this problem.
Yeah, no, it's not a generic miracle. It so happens that here it is true for any order in perturbation theory.
So if you try to sum the epsilon to the ny,
It is not going to work in the y-in.
Okay. Yeah. Okay.
Okay? So this was for the y-out. Now, what's happened for the y-in? The y-in, remind you, is y double prime plus y prime plus epsilon y prime plus epsilon y equals 0, where y of 0 is 0. Well, here everything is a function of x tilde, not of x. Okay? Good. How do I continue from here? Again, I will put y0 plus epsilon y1, and I will collect terms. So clearly, for epsilon to the power of 0, I will have y0 double prime plus y0 prime equals 0, right? And the solution will be b times e to the minus x tilde minus 1, exactly what we find here. Because this was the zeroth order in the perturbation, right? What will happen for epsilon to the first power? Right, so you can see here and here I will get the 1 contribution, and here I will get the 0 contribution.
Correct.
Right, so I will get y1 double prime plus y1 prime plus y0 prime plus y0 equals 0. Right, well, y0 prime is, okay, y0 is that. Okay, and we have now y of 0 is 0. Okay, but y1, but this is true also for y. I mean, what now? All the y's are 0 because this is the boundary condition, and so what we have is y1 double prime plus y1 prime plus the minus b e to the minus x tilde, this is this one, with a minus because I took the derivative, plus b e to the minus x tilde, right, minus b is 0. I just plug this into that, and this cancels that, I hope. So we have something, right? And we can solve this and so on and so forth. So this is just to explain how to extend it to higher, to extend the treatment to higher order in perturbation theory. And you can play with it. I mean, usually nobody is taking it to higher orders, but if you want, you can expand it in higher orders in epsilon. Yes?
This is a specific problem that everything from the first order onwards cancels out in both y and
Yes, yes. Okay, so this is...
No, that's fine. But are the problems that you have, like, I guess it's rare for something to exactly equal 0 for this and all others. So I guess are the problems that, like, from the first or from the second order things start to 0 out, or from the third order?
Okay, let me give the next example. Okay. So this was a specific problem, completely pedagogical. pedagogical, whatever, completely pedagogy, with absolutely no importance because we have the exact solution and the right. And so very specific. Now, in order to convince you that you have learned something, let's consider the most a very generic problem, right? So now let's consider an extremely generic problem. Yes, and the problem is epsilon y double prime plus a of x y prime plus b of x small b y equals 0, where y of 0 is a and y of 1 is b. See, clearly this is the most generic second order equation, linear second order equation, homogeneous second order equation. But you know, it includes Airy, Bessel, Schmessel, all the equations that you have encountered in MEMP3 and many others, and equations that you can imagine. Yes. So this is completely generic, and of course it's equivalent to Schrödinger equation and to whatever, many other things, right? Now, it so happens that epsilon is a small parameter, right? For example, in Schrödinger equation, h bar sitting here, this is in many cases a small parameter, okay? And you want to get some approximation to this solution as epsilon goes to 0. You want to find the asymptotic behavior of the solution as epsilon goes to 0. How we are doing that? Okay? So first of all, you have to divide the system into the inner and the outer regime. Right? And I would like to assume, later we will relax this assumption, I would like to assume that a of x is larger than 0 when x is between 0 and 1. So a is positive. This is all I'm asking a to do. Be positive between 0 and 1. Okay? And I will decide to divide the system in a way that this region will be y out, and this region will be y in. Okay? Now you're asking me, since it's completely arbitrary, why this is out and this is in and not vice versa. I will explain it later on. But for the moment, please accept. Okay. So what I'm doing in the outer regime, as explained, in the outer regime, I simply take epsilon to 0. Okay, so in the outer regime, what I have is, in the outer regime, I assume that epsilon is 0. So my equation is a of x y prime plus b of x y equals 0, with y of 1 being b. This is a very simple equation. Why? Because now we are in the realm of first order equation, and this is an exact equation. So I can write that dy, dy dx is b minus b of x over a of x times y of x, right? And dividing by y, so dy over y is minus b over a dx, and I should integrate both sides. I will find that ln y is minus the integral up to x of b of t over a of t dt, generically, right? Of course, it's independent of the lower bound of the lower limit of the integral. Why?
Because we're in the
Because it's just a constant, right? And in any case, I can add here a constant, right? Okay, so y will be a, or e to the a, whatever, but the important e to the minus the integral b of t divided by a of t dt up to x. But this is up to a multiplicative constant. Okay? Now, I have to satisfy the boundary condition that y1 will be equal to b. Okay? How do I do that? Very simple. I will write it as b times e to the minus the integral from x to 1 b of t over a of t dt. You see the trick? First of all, I can move it from the upper to the lower bound. It doesn't matter because it's again a constant, right? And now when x is going to 1, this is 0 and I have b, and everywhere else I have something, right? So this is the solution. This is y out. So I solved for y out. Okay. Now, so the y its outer regime is to some extent simple because I assume that epsilon is 0 and I have a first order equation. This is that.
Shouldn't B be 1?
Hmm?
The larger B.
It's a generic constant.
I mean, I asked it y of 1 to be b.
Oh, okay, yeah, I see.
Now, okay, please delete this a because this a, I mean, I decide
Yeah.
here it stands for a constant and here it stands for the left boundary condition. Okay. Now, so now what's happened in the inner regime? So we are using our old trick. What we are doing, we will define x tilde to be x over epsilon. And now we can write that epsilon over epsilon squared y double prime, it's a different y, this is a y in, plus a of what? A of x tilde of epsilon x tilde, epsilon x tilde, which is x, time divided by epsilon times y prime, plus b of epsilon x tilde divided, not divided, times y equals 0, where y of 0 is a. Now, okay, so this epsilon cancels with this one, right? And I can multiply everything by epsilon, and I will get y double prime plus a of epsilon x tilde y prime plus epsilon b of epsilon x tilde y equals 0. So, first of all, and now I can use, I will implement the fact that that epsilon is small, right? Because x tilde is order 1. I assume that x tilde is order 1, and epsilon is still small, so I can do two things. One of them is to neglect this term, but I can have also another trick that will make my life much better. Because if x tilde is small, is order 1, and epsilon is small, then this is a small, very small number. So I can expand this in a power series. And I can take only the leading order. So assuming that A have a series expansion around around 0, and that it's so what we get is y double prime plus a naught y prime equals 0. Right? Well, a naught is simply the zeroth order expansion of a around 0. Okay? So if a happens to be x cubed, then this is wrong. Right? But if a is if a is a normal function at 0, then it will have some value, which is non-zero. Yes.
You need to assume that A has a series expansion around 0. It needs to be an additional assumption on the
I'm taking the leading order,
No, okay, but
and I assume that the leading order is a constant.
no, that's for sure. But I guess it's a more general question. But if you have a function, if A didn't have a leading order at 0, would that solution of the
Give me an example.
1 over x? I don't know.
A is 1 over x. Yes,
So,
then I'm in trouble.
No, but
That's especially because it's singular point.
yes, but אוקיי, אני אשאל בעברית, סליחה. יכול להיות לי מצב של-A יש נקודה סינגולרית. ל-A אין פיתוח של טור סביב 0, אבל הפונקציה של המאדר שהיא פותרת תהיה. זה לא כאילו פוסל לי אוטומטית את המאדר, זה לא כאילו פוסל לי אוטומטית את Y. שיהיה לה איזשהו פיתוח סביב X.
לא חייב להיות. יש משוואות שיש להם 1 חלקי x כאן.
ועדיין הפונקציה...
ועדיין יש פונקציה... מה עושה... האם זה בעצם כל ה...
האם זה מדבק? זו השאלה. האם כאילו המקדם לא מתנהג יפה ב-0?
לא, כי אם יש לך משוואה מהסוג y תגיים פלוס y tag over x plus y over x squared equals 0.
אוקיי.
Right?
זה מתנהג יפה?
This is a yes, and you know that the solution
נכון.
is y equal. The solution is y is something like x to the power of r.
כן.
And then you have the characteristic equation is r minus 1 plus, I mean, here you have a constant, okay,
כן,
it's
פלוס
a and
R,
b,
פלוס
right?
R.
Plus a, r plus b is 0.
אוקיי.
So, I mean, this is an equidimensional equation, it's completely kosher. You
And-
have
And you can do this Y in stuff.
two solutions, but no, but this is just because it is equidimensional. If now you have here a function that have, 1 over x plus x times y prime, then it isn't working anymore.
Sure.
And you can analyze it close to a then you have an assertion singularity, and you can analyze you can analyze it at the vicinity of the singular point by the techniques of the local analysis, right?
Okay.
But not yes. So
So there, A is bigger than 0 always, right? So it's the only condition. It works
no,
for
here I assume something else. I also assume that A is not 0 at 0. Okay, maybe it's bigger or equal. I don't remember. Okay, fine. So I assume that, and this is now that's an easy problem. Because again, I will have an equation with constant coefficient, right? And such an equation and I will plug our universal solution. Right? I will plug our universal solution. Y is going like e to the alpha x, so I will get alpha squared plus a naught alpha equals 0. That's a characteristic equation when I plug it here. Okay? And I will get alpha x tilde, of course. And I will, so alpha is either 0 or minus a naught. So the generic solution of the inner solution is a e to the minus a naught x tilde plus, oh wait, no. This is C1 and C2, right? Not to mix it with the boundary conditions. And I want the y of 0 to be, I want y in of 0 to be a. And therefore what? Therefore, C1 plus C2 is a. So C1 plus C2 is a, and therefore C2 is a minus C1. So I can write y in as C1 times e to the minus a naught x tilde minus 1, I guess, plus a. Okay? So this is a general form of the inner solution. This is a general form of the outer solution, and what remains is to match it in order to find what C1 is. Right? I wanted to know what C1 is. So what I'm doing, I'm asking what is y out when x is much smaller than 1. And this is simply b e to the minus the integral from 0 to 1 of b of t over a of t dt. And I will ask what is y in when x tilde goes to infinity, right? And this will be what? This will be a minus C1. Okay? And therefore, I want this to be equal to that. So it implies that C1 is a minus b e to the minus the integral from 0 to 1 of b over a dt. So when I plug it here, what I should do, I should plug it here. So therefore, the final form of y in is what?
The a's cancel.
How could it be? No. C1? No. Okay, so I have a times that minus a plus a. So this one cancelled with that, and I will get a times e to the minus a naught x tilde.
But there's also contribution from.
Yes. Okay, this is from the a. And now I have the b. I should put the b here. So I will have plus b 1 minus e to the minus a naught x tilde times e to the minus the integral from 0 to 1 of b over a dt. Good. Now what I should do is to, okay, this is the y in, this is the y out. Double check what happened when x tilde goes to 0. Then from this I will get a. And from this I will get nothing because this will be 1 and 1 minus 1 is 0. Okay? What happened when, okay, so this is the y out, this is the y in, and the only question remains is what is y uniform. So y uniform is y out plus y in minus the overlap. Minus z, actually. Right? So we have, wait, no, this is y out. Okay. So this is y out. Okay? So y out is b e to the minus the integral from x to 1 of b over a dt plus y in, which is a e to the minus a naught x tilde plus b 1 minus e to the minus a naught x tilde. By the way, x tilde again, if I'm putting it here, it's x over epsilon. And I have to subtract z. But if I'm subtracting z from this, what I will get, here it's from 0 to 1, and here it's from x to 1. So the subtraction will give me, okay, let me write it, minus b e to the minus integral from 0 to 1 b over a dt. Note that this minus z is the integral from 0 to x, I guess. Something like that. Okay? So, fine. So this is the uniform solution. Now, to remind you, when we just started, I wanted you to trust me that y out is this region and y in is this region, despite the fact that the equation is completely generic and has nothing to do with how do I know that I shouldn't do it the other way around, right? Why I don't neglect the epsilon at y in and do this transition to x tilde at y out, right? There is a reason for that, and the reason was this condition, because if a naught was negative, right, then this was an exponentially increasing function, and it implies that if we now want to match, we cannot match. In order to match, we want the inner solution either to reach a constant, right? Both solutions actually. Either to reach a constant in the matching region or to go to 0 or something like that, right? We cannot allow ourselves that one of the solutions will diverge in the matching region. If both of them diverge, it's not a matching. So because we assume that a is larger than 0, then we were able to know in advance that that this should be the inner and this should be the outer. And of course, if a is smaller than 0 all over the place, then we should switch. Yes?
But because of the approximation we did for a as a series, it's just a0. It's just a at a value at 0 that needs to be positive.
Yes.
Not the entire value of a from 0 to 1. Like you said.
No.
There.
The reason why I assumed that it has to be, it should not change sign in the entire region,
Okay.
there is another reason that I will explain next lecture.
Okay.
For the moment, I only said that because you have to divide this into two conditions. One of them is A, do not switch signs in the segment we want to analyze.
Okay.
This is something that have importance.
Next step.
I will explain it next time.
So
You can see it immediately.
So
Because if H changes sign, then you have a problem here.
okay. Yeah.
Then this integral diverges.
You have to do an integral before and after. And
Yeah, this is a headache, right?
Okay, so a can't change
A
sign. then
cannot
at
change
0,
sign.
And at 0 it has to be positive, so it always has to be positive.
And so either it's positive in 0,
Okay.
either it's positive or on the entire segment, or it's negative on the entire segment. If it's positive on the entire segment, you have to take the inner to the left. If it's negative in the entire segment, you have to take the negative to the right. The inner to the right. That's a story.
Sure.
Now, perhaps it will be of interest. So, interestingly, all this story of the boundary layers, as far as I know, came from the theory of aviation. You know, when the airplanes were invented, people have a lot of interest in aviation. In particular in Britain, because the headlines of the newspapers were saying that Britain is no more an island. The enemy can arrive now. I mean, no matter how good is our fleet, we are exposed to aerial invasion, and both it was years before World War I. So all the powers of the time were in a arms race, and they tried to develop better and better airplanes in the standards of these days. And there is a problem, because in order to understand how the damn thing is working, you have to understand what is the source of the lift force, right? Why the airplane is staying in the air, right? And the reason why it is staying in the air is because you have a turbulence going like that, right? And so here above the wing, how does it go?
It goes.
I mean,
Pressure gradient.
This generates a pressure gradient that generates a lift. But you have a turbulence going around the wing, right? I don't remember if I have to. Okay.
No, it is like that.
Now, to conclude that there is such turbulence, you have to look at the equations for fluid flow, right? And the equations of fluid flow, you know that they have a viscosity term, right? And with the viscosity terms, they are known as Navier-Stokes equation, and what is also known is nobody knows how to solve them, right? Without the viscosity term, it's, I don't remember the name of the equation, but it's much simpler equation and you can solve it.
Euler.
Hmm?
I think Euler equation.
Euler, yes. So it's linear, it's still non-linear, but you can solve it. And you can find the turbulence. This is a legal solution of the equations without the viscosity, right? However, without viscosity, you cannot generate a turbulence. I mean, if you take your cup and your spoon and roll it in your tea cup, the only reason why you generate a turbulence is because of viscosity, because of friction between the spoon and the liquid. If there is no friction, then you can do something like that with a spoon, and you cannot generate turbulence. So the only the origin of this flow must be originated in the wings of the airplane, right? Through the effect of viscosity. So the British government, or who knows whom, who took the decisions at the time, decided that they will not build any airplane before understanding exactly what is going on physically. So they have a committee of very talented scientists, but of course they did no progress at all, because you cannot solve the Navier-Stokes equation. The Germans were more practical. They asked for engineers to build something that fly no matter how. And for that reason, they have, at least at some stages of the war, they had better quality of Air Force, although, you know, in Great Britain there was some still engineering motivated research that, by the way, Einstein, despite being against the war, in 1916 he planned an airplane for the German army with a very sophisticated wing shape, and because he was not an engineer but a physicist, damn thing never it cannot fly. But in any case, or maybe it flies but miserably, worse than other wing But in any case, there was what's the name of the guy? I mean, there is a number, like Mach number.
Reynolds.
No, not Reynolds, not Mach, but the one that is connected to boundary layers.
The one that says if it's viscous or not. It's Reynolds number.
No. There is a Reynolds number, but there is another number.
Stokes?
No. I've forgotten.
מצינו את כל הקונספיטור.
מה? No, there are way many numbers in the theory of fluid mechanics. It's something that is very hard to pronounce. I don't remember for the moment. You can check on your. You can ask whatever Google or something. But this guy understood that what you really want is what you really have to understand is that all the activity that has to do with viscosity happens in the boundary layer of the wing, right? And you want to neglect it and to assume that you have some source of turbulent flow, and from now on, when you are farther away, when you go a few centimeters or a few meters from the wing, you can forget about the viscosity term, and then you can solve the equation. This was the basic insight that all the interesting activity, although you must have the viscosity in order to generate turbulence, it happens in a layer of negligible width. And I wonder if even today they know how to analyze what is going on there, except of a few thumbles of engineers. But this allows them to achieve some progress. And so, nobody here have a cell phone? What is
It's the one you said before. Is it Prandtl number? Because you said it's how to pronounce.
Again?
Prandtl.
Prandtl, yes. Prandtl.
It has a T in it. It doesn't make
Yeah,
sense.
it's. I mean, the point is that it has no vowels. Just like my surname Snarb is also suffered from the same effect, although it's less. Prandtl, yes, something. Yes, Prandtl, Prndtl or something like that.
Yes, exactly.
Okay, so if you know how to pronounce it, please. Ask for German citizenship, but the idea is that from then on, from his work, people have become people realize the importance of boundary layer theory, which is now used for many other things. And the idea is yes that you can bridge between the inner region and the outer region by the using the technique of asymptotic matching. And next lecture we will elaborate a little bit on other examples, two other examples of asymptotic matching before moving to WKB technique. Thanks. כן.
לא קשורה בשיעור.
לא קשור.
share. Okay. Hey.
Hello everyone, welcome back. Today we will solve a lot of problems about boundary layer theory. So let's first of all recap the main algorithm that we will use today. So first of all, for this second order linear differential equation, we need to figure out sign of a of x, of this coefficient. So if it's positive, then the boundary layer is at x minimum, and x min and x max, they're just boundaries in the problem. In most of the problem, the boundary is 0 and 1. So, and if a of x less than 0, so boundary layer is at x maximum. Then after we locate the layer, we need to solve this equation for inner and for outer region. And for the outer solution, we just plug in epsilon equals 0 and solve the first order differential equation. For inner region, we rescale our variable x to some new variable, inner variable. So I divide x by delta. In most cases, delta equals epsilon. But today we will see problems that delta is not equal epsilon, but epsilon in some power.
It's a function of epsilon.
Yes, it's function. Usually it's just epsilon. But there are problems that it's epsilon to the, I don't know, 2/7. So it can be some strange power. Okay. Then we know inner and outer solution. We mesh them using x for inner solution. The inner variable x tilde goes to infinity, and for outer solution x goes to 0, and this is match, y match. And the final step is to write the uniform approximation, which is sum of inner and outer solutions minus y match. That's it. Okay. Yeah, today we will solve a couple problems with finding leading order uniform approximation and some problems with the next order approximation. Okay, let's start with problem number 1. It's epsilon y double prime plus cosh x times y prime plus minus y for 0, and the boundary conditions are y of 0 equals y of 1 equals 1. So as you can see, x goes from 0 to 1. Epsilon, some small parameter. Okay, so now, and we need to find the uniform approximation in the leading order. Okay, so let's first of all, let's understand where is boundary layer. We need to look at this coefficient in this region and say whether it's positive or negative. So I think it's pretty obvious that this hyperbolic and cosine is positive in this region. So therefore, our inner layer located near minimum x and the outer layer near the x equals 0. Okay, so now let's start with outer solution. For outer solution, we, for the leading order, we plug in epsilon equals 0, and we end up with hyperbolic cosine times y prime equals y. Okay, now let's integrate it by parts. So we'll have ln y equals integral the x over hyperbolic cosine. Okay. So we I can multiply both numerator and denominator by hyperbolic cosine. Okay. And have hyperbolic cosine times the x. And here I can use the
1 minus 1 plus.
it's 1, right? Then I can write it like this. X. Okay. Then I change my variables, write it as dt. Here is 1 plus t squared, right? And this is known integral. Yes, it's arctan of t, and t was sine, hyperbolic sine. So it's arctan of hyperbolic sine of x plus some constant of integration. Okay, so now I know that
Boundary condition.
I need to plug in the boundary condition, and I know that
Take the left one.
x should be, if x equals 0, my ln of y should be equal to 0. If x equals to 1, because if y equals 0, ln of y is you get it. So therefore I should write c is minus arctan of hyperbolic sine of 1. Okay. Then I plug in, should be exponent to the arctan of hyperbolic sine minus arctan of hyperbolic sine of 1. That's my outer solution. Okay. Now let's find inner solution. I need to rescale my x variable. X for epsilon. Okay. And rewrite this equation in terms of new variable. So I'll have epsilon divided by epsilon squared y double prime of x tilde plus hyperbolic sine of epsilon x tilde divided by epsilon times y prime of x tilde minus y of x tilde equals 0. Okay. Then I can multiply both sides of the equation by epsilon. Have because x tilde is order 1 and this is small, I can expand the hyperbolic sign, and because we only interested in leading order approximation, I can just simply set it. Yeah, first order, leading order, it's the same. So I can say that this is, for our purposes, it's just 1. Okay, and therefore, for the leading order, I will have y double prime of x tilde plus y prime of x tilde equals 0. Okay. And the general solution of this equation is c1 plus c2 e to the minus x tilde. But then I need to use my boundary condition, and if we use it, I have c1 plus and 1 minus c1 e to the minus x tilde. So, and you can see if x tilde is 0, I'll have just 1, as it should be. Okay, now we know inner solution and outer solution. Here is outer solution, here is inner solution.
There is epsilon. There in the final term there is minus epsilon y. Okay. You neglected this term, the final term. It's small. Okay.
It's leading order, so yeah. Okay, now let's find the matching solution. Okay, so in inner region we need to find the limit then x tilde goes to infinity. Okay,
It's c1.
and we will have just c1, and in this region x should go to 0, so therefore this is just 0, and we end up with e to the minus arctan of sine hyperbolic sine of 1. That's our c1. Okay, and the final y is formal. Okay, we should add inner and outer and subtract c1. And because in the inner solution there is c1, I can just write the sum of those without this term, and that would be the uniform approximation. So e to the arc tan of hyperbolic sine of x minus arc tan of hyperbolic sine of 1. Okay, this is outer approximation, and plus this term plus 1 minus e to the minus arc tan of hyperbolic sine of 1 times minus x over epsilon. I mean, I can make it look nicer, but you get it. So it's minor changes. Okay, let's move forward. Again, we need to find leading order uniform approximation for this equation. With the boundary conditions that are the same. X goes from 0 to 1. Okay. So again, let's start with the outer region, because this A coefficient is always positive in this region, so therefore our boundary layer is near the point x equals 0. So for outer region, the equation that I have is y prime divided by y equals x cubed divided by x squared plus 1. Yeah, this is just a 0, okay? And the rest is here. So again, I integrate, and left hand side is ln y, right hand side is integral x cubed dx divided by x squared plus 1. Okay, here I can do the same trick. 1/2 x squared dx squared divided by x squared plus 1. Then I rename x squared by t. Okay, and now have 1/2 t dt t plus 1. Then I can do the trick with 0. I can write it like this. Right? I added 0. Then I have just integral of dt, right? Minus 1/2 integral of t plus 1. Okay. The first one is just 0, 2, and the second one is minus 1/2 ln of t plus 1 plus c. Okay, now let's find c.
Go back to the x now.
First of all, we need to go back to x, but anyway, I mean, it's one, either t or x, but yeah, better to go back to x. So y of x is exponent, there is x squared over 2 minus 1/2 ln x squared plus 1 plus c. And at x equals 1, all of this should be 0 to y equal to 1. Okay, so 1/2 minus 1/2 ln of 2 plus c should be.
Can we pull out the natural log of x squared plus 1?
Yeah, sure. Then
You can, but
it's the same. It's just definition of the logarithm, right?
yeah.
So we finally write it down. So c therefore is, let's find it. Exponent x squared over 2 minus 1 half ln x squared plus 1 plus 1 half ln of 2 minus 1 half. Okay. And we can rewrite it as e to the x squared over 2. Let's write it like x squared minus 1 over 2, right? Then this logarithm is to the square root of x squared plus 1. And we also have this, so, okay. Yeah. So finally we found the outer solution. Okay, now let's find the inner solution. Okay. So we rescale our x variable, and the new equation will be 1 over epsilon double prime x tilde plus epsilon x squared plus x tilde square epsilon square plus 1 times y prime x tilde minus epsilon cubed x tilde cubed times y x tilde equals 0. Then we multiply both sides of the equation by epsilon, and finally we get 4th power here, and the rest is the same. Okay, and because we're looking for least node approximation, we're only interested in terms without epsilon. So that's why we finally obtain the same equation as before, with the same initial condition, not the initial condition, boundary conditions. Therefore, we can just copy the last result. So x of phi of x tilde is c1 plus 1 minus c1 e to the minus x tilde. That's inner solution. Okay. Now to the first step. First step, we're gonna match them. For inner solution, again, just c1. For outer solution is square root of 2 e to the minus 1 half. Or, yeah, let's keep it like that. Okay, so we find it, then our uniform approximation is this guy. Okay, so let's write it 2 over x squared plus 1 times e to the x squared minus 1 over 2.
That's the bracket.
Hmm?
That's the bracket. 1 minus c1.
No, I first write the outer, then plus without this c1 because we subtracted. that's our leading order uniform approximation. Any questions so far? Now let's make our life harder and find the next approximation to leading order for the uniform solution, uniform approximation. The equation is the following. Epsilon y double prime plus 1 plus x squared y prime plus y equals 0, and the boundary conditions are the same. But we need to solve it up to order of epsilon, so our uniform approximation should have the same, so this term plus epsilon multiplied by some other term. So therefore, because we need more terms, for our solution we will not blindly set epsilon to 0, but we will write it like this. So our outer solution is y naught of x, exactly leading order approximation, plus epsilon times y1 of x, next order correction. And then we plug in this into the equation, and we will solve two differential equations for leading order and for next order correction. Okay? So we'll have epsilon y not double prime of x, and I keep here terms only up to epsilon. I don't need epsilon squared and the high terms. So plus 1 plus x squared and y naught prime plus epsilon times the same, but y naught prime, y1 prime, sorry, and then plus y naught plus epsilon y1 should be equal to 0. Okay, now let's solve for the leading order as we did before. So for the leading order we have y naught prime over y naught is minus 1 over 1 plus x squared. Right, then ln of y naught is minus this integral. And that would be 1 over 1 plus x plus c. Okay, now let's find c. So then x equals 1. This sum should be equal to 0. So therefore 1 divided by 2 plus c equal 0, and c is minus 1/2. Okay, so our leading term in outer solution is exponent 1 over 1 plus x minus 1 half. Okay. Now let's go to the next order correction. So to the epsilon to the first power. What do we have? We have y naught double prime plus 1 plus x square y1 prime plus y1 plus y1.
Wait, what is the first term y, the first term y0?
Because we collect terms with epsilon to the first power.
Oh, okay.
And here epsilon.
Okay, now I see.
Okay, because we know already what is y naught, it's some known function, right? And this is first order equation. We can use, for example, integrated factor, yeah, to solve it. And let's do it. So let's rewrite it a bit. So we have y1 prime of x plus 1 over 1 plus x squared times y1 of x equals minus y naught double prime. Okay, then I need to multiply it by mu of x. Then I eventually get the differential equation for mu, and mu of x will be e to the integral of this stuff, right? So it's the x over 1 plus x squared, right? And we already did it. So it's e to the minus 1 divided by 1. Right? So we know now integrated factor. Then we can write the final solution for y1, right? y1 of x will be 1 over mu, so e to the 1 plus x times integral of mu, which is e to the minus 1 over 1 plus x times right hand side, but right hand side was with minus sign, right? So we need to therefore add minus here. So, and let's calculate the second derivative of this. Okay, so y naught prime is minus exponent, right, divided by the derivative of this, no, multiplied by the derivative of this, and it's 1 plus x squared with minus n. And the second derivative, so again, let's firstly find the derivative of this and add derivative of this. Okay, so derivative of this gives us the same thing, so, and we will have add one more minus, so therefore we have exponent, okay, divided by 1 plus x to the fourth, or to the third, yeah, third. No, fourth.
There's one
because
that's a third and one that's a fourth.
Yeah, if I take the first derivative of the exponent, I eventually have the same. So that's why this is fourth, and then I need to write plus derivative of this. Okay, so, and the derivative of this is 1 plus 2 times exponent times 1 plus x to the third. Yeah. Okay. So now I need to plug this to the integral, right? And you see that in the exponent, let me write it explicitly, I have 1 plus x minus 1/2, 1 over 1 plus x minus 1/2. You see, then I plug this y double prime to this exponent and this exponent, they cancel out, right? So, and the only thing that I left in the exponent is minus 1 x e to the minus 1/2. So I can move it out of from the integral, right? So let me write it minus 1/2 here, and inside the integral I have this this simple stuff. So 1 plus x to the 4th plus 2 1 plus x to the 3rd, but I need to. Oh, that's it. Oh, I think I forgot something. I forget something. Prime. Times mu. Oh, I think that's fine. And then plus c divided by mu. So, and mu, constant of integration, right? So e to the
Plus
1 plus x. Okay. Now, after we integrate this, so, and plug in the boundary condition, which is y1 of 1, 0, we end up with this solution for y1. y1 is e to the 1 plus x minus 1/2 times 1 over 2 1 plus x to the 4th plus 1 5 plus x to the 5, sorry, 4 is here, and minus 3 over 8. Yeah, I think, yeah. Then I go from this line to this line. I divided both sides by this factor, right? And therefore, this should be also divided by this thing. And therefore, inside the integral, I need to also divide each by this. So the final power will be 6 here and 5 here. And now you can see that it's exactly matches after one integration to this. Okay. So, good. We found y naught, which is this, and y1, which is this. This is for our solution. Now let's work with inner solution. We do the same stuff for inner solution, but with the new variable, with x tilde. But the rest is pretty much the same. So I rescale my variable x to x tilde. And x tilde is x over epsilon. Okay. And now let's solve this for y naught and y1. So let's rewrite this equation and plug in this. So we'll have 1 over epsilon times y naught double prime of x tilde plus epsilon y1 prime of x tilde at the first term, then plus 1 over epsilon times 1 plus x tilde epsilon squared times y naught of x tilde plus epsilon y1 of x tilde. This is the second term, and plus the first one, which is just y naught of x tilde plus epsilon y1 x tilde. All of this equals 0. Okay, now let's carefully find the solution for y naught and for y1. For the leading order, what do we have?
Why not double prime? Plus why not?
Okay, let's firstly
Expand.
let's firstly multiply again each side by epsilon, okay? Because this is the correct procedure. If we multiply it all of this by epsilon,
mistake there. It's supposed to be y not tag the second term. So that the yes.
thank you. Yeah, thank you. So after we multiply both sides by epsilon, we will have epsilon here and epsilon squared here. And we can throw it because we only care of the terms that has epsilon to the 0 and epsilon power. Okay. Now let's write the leading order approximation. So y naught double prime of x tilde plus 1 plus x tilde epsilon squared times y naught prime of x tilde equals 0. And again, the leading order approximation here will be just 1. Okay, that's why I can erase it. And again, we see the same usual equation, right? So that's why y naught of x is just c1 plus 1 minus c1 e to the minus x dot. Okay, this is the leading order. Now let's go further for the next order correction. For next order correction, we have y1 double prime x tilde, then plus, and here we should be careful
1 plus.
because let's expand this. Okay, will be
1 plus
1 plus 2 x tilde epsilon. So, and when we multiply this by this, we have epsilon. So therefore, we need to include this term into this solution, into this equation. So it will be 2 x tilde y naught prime of x tilde. Okay. And we also have this term multiplied by 1, which is also order of epsilon, plus y1 prime of x tilde plus y naught x tilde, all of this equals 0. Okay, again, because we know that what is y naught, so all of this is just some functions, known functions. All we need to know is to solve these inhomogeneous second order differential equations with constant coefficient. This is our first order solution. Okay, so we know what is the solution of homogeneous equation. It's the same, right? If this and this just 0, this equation has the same solution. But this is homogeneous. We need to add to the homogeneous solution the particular solution of the inhomogeneous equation, right? So therefore, let's write it like this. For homogeneous solution, we have y1 of x is, let's call it C2. Let's call it like this, plus C2 e to the, not the same, because the initial, not the initial, but the boundary condition would be 0, not 1 in this case, for y1. So therefore, let's do the general solution like this. Okay, and then let's look at the right hand side. Okay, because we can try to guess what is the particular solution if we know what is the right hand side. So yeah, let's find it. We have in the right hand side of the equation we have minus 2x tilde. Then we need to multiply it by derivative of this, which is 1 plus x all the square, and here should be plus, therefore, right, to the exponent.
It's
the
the
blue one.
Oh, yeah, yeah, I missed it. Yeah, thank you. So it should be minus 2x tilde. Then the derivative of this is
plus
1 minus c1 e to the minus x tilde, and then minus this one, minus c1 minus 1 minus c1 e to the minus x tilde. That's the right hand side. Okay, so what do we see here? We see constant. Okay, we see exponent times constant, and the first order polynomial times the exponent. I mean, we can split it because we're solving linear differential equations. We can easily split those two by 3 partial solutions to each of them, right? So what will be the partial solution for C1 of this equation? But just C1. If you have in right hand side of this, this plus this equals C1. What is the solution? Particular solution.
just polynomial.
Minus C1.
Just polynomial.
6 squared.
Minus C1 x tilde. I mean, if you plug this to this, the second derivative is 0, and the first derivative is just minus C1. So that's why for this, the particular solution is minus C1 times x tilde. Okay, now let's do for this. We need to be careful here. Why? Because this and this, they have, which is called resonant term, because we have the same exponent in the general solution of the homogeneous equation, and here is in the right hand side we also have the same exponent. So that's why when we guess the solution we need to multiply it by x tilde. So because this is just exponent times constant and its resonant term, we will guess the particular solution as some constant a times x tilde times the same exponent. This is for our guess for this. And for this, what do you see here? First order polynomial times the exponent. So therefore our guess for the solution will be first order polynomial times x, because of this resonance, times the exponent. Okay, and by plugging in this and this to the, we will do it separately, right? But if you plug in this to this equation, you finally find a and b. Okay, and then if you do the same thing for this, you find what is the a constant. Okay, but to save the time, I write it down because you know all of this from your undergrad course, so it's waste of time to do it right now. Just a second. Yeah. So let me write the particular solution. Those two. That's the solution. And then we need to apply boundary condition, which is y1 of 0 should be 0. Okay. So this is 0, this is 0, and we end up with C2 plus yeah, it should be force 1. But then I will confuse it with this. So let me call it B1 and B2. Here is C1. Or no. Okay. And now I have B1 plus B2 is 0. So therefore, if we use the boundary condition, y1 finally of x tilde is b1 times 1 minus e to the minus x tilde. Okay. Then minus b1 x tilde, the rest is the same. Okay, now we can finally match. Okay, we can do matching. Our first step. Let's do matching. So red one is our outer solution, blue one is our inner solution. Okay. So we know that outer solution goes to x goes to 0. So outer solution limit is e to the 1/2. This is order of the first order, leading order, right? And for the next order, e1/2, and then times some constant. Too lazy to calculate. I mean, it's 53 over 80. Okay. So this is for outer solution, and then for inner solution. X tilde goes to infinity. So C1, right? Then epsilon times this, and let's be careful. So plus epsilon. Then we have B1, right? Minus B1 x tilde, and the rest is 0 because exponent goes to 0 faster than x goes to. Okay. You see something wrong?
You have too many
X
C1, B1.
We have to
X
unknown.
X tilde. I mean, let me write it like this: C1 plus
B1
epsilon B1 minus, what is epsilon times x tilde?
It's one number.
It's just x.
Mhm.
Because
Oh,
we
okay.
rescale it
Oh,
like this, so it's just x. So B1 times x. And you see that in the leading order, now we have strange situation. We need to equal constant to C1 minus B1x.
No, you do P1 equal to e to the power half.
B1.
Because- Yes.
Why?
No, you have epsilon multiplied by B1, and there you have epsilon multiplied by e to the power half. I have the x. No.
Yeah, but I mean, the point is, here I don't have terms of x, and here I have. So what should I do?
No, but you.
I
you
cannot
say
match
E1
them
is
because-
zero. You say,
B1 is 0.
no, you say x goes to
No,
0.
it can't be 0. Because if
Maybe
you
the
match
de-
it
the
with the
degree of,
next order, it should be this, exactly, to match that.
Maybe x tilde shouldn't be x over epsilon.
No,
No, you go.
that's right.
You match the both, so x goes to 0. So you have without the P1.
No, why? Here is x tilde goes to infinity.
It's okay, but you say that you have to match the two equations.
X now is just arbitrary number between 1 and 0. We cannot neglect it.
Okay.
So what should we do? We need to correct this term. How? Let's look at y outer 0th order. So instead of just plugging in x equals 0, we will write Taylor expansion of this and add next term correction. So the first term of the Taylor expansion of this will be e to the 1/2. But we also add the second term. Okay? So the first term, the next goes to 0 is e to the 1/2. Then we need to add plus the derivative of it in the x at the point x equals 0. So the derivative of this is minus 1 plus x squared, and this all of this. And we need to multiply it by x. Okay, so x equals 0. So we just add second term of the Taylor expansion, and therefore we'll have here minus e to the 1/2 times x. Okay. So now we can match. So C1 is e to the 1/2. We have here C1. Let's write it like this. So C1 minus B1x equals e to the 1/2 minus e 1/2 x. Okay. Just a second.
To which
Yeah, I see.
there is no B1x because we talking about the leading order of epsilon.
It's B1 minus B1.
B1x is not
Yeah.
It's B1. Let's see.
Okay, so this is C1, right? And B1 is this. Okay, and then you subtract, you sum the inner solution and outer solution, subtract the match, and you finally will get these two lines answer. Okay, so yeah, you can see it in the tutorial notes. Okay, good. So we have some time to show you the example. Then scaling is different, so not x over epsilon, but different. Let's look at this example. So again, in the region then x goes to 0 to 1, this coefficient is only is positive. But there is a point at x equals 0 that then this coefficient is 0. Yeah. It's not really singularity because the equation at this point is okay. Yeah, but it will change the scale. In the previous examples, the coefficient before y prime will always positive. Always positive. So that's why we have this nice scaling for inner variable. X tilde was equal to x over epsilon. But now this will not work, and we will find the proper scaling. By the way, this is from the exam. This.
Next exam?
Hmm?
The next exam?
No. I don't know. Maybe I don't know. But this is for some exam. I don't remember. Maybe 2 years ago, 3 years ago. Yeah, and thank God we need to find on leading order solution. So yeah. Okay, let's start with outer. For outer, we have x 3 over 4, y prime minus x to the 1/4 y. Okay, so 1x, 1 y of x is minus, so we need to divide it by 3, so it's x to the minus 1/2, I guess, the x integral, and it's x 2 square root of x plus c.
Minus
There is minus.
Okay. Now let's use the boundary condition, and we have minus 2 plus c equals to 0, so c is 2, therefore our solution is e to the minus 2 square root of x plus 2. Okay. Now let's work with in the solution. Let's rescale with some delta, and rewrite this equation in terms of new inner variable. We'll have epsilon divided by delta square y double prime x tilde plus x to the 3 over 4 divided by delta y prime. Yeah, it should be this and epsilon times delta here and times epsilon to the same power. Okay. And plus epsilon, not epsilon, delta. Epsilon x to the tilde 1 over 4, epsilon to the 1 over 4.
Why it's epsilon? It's delta.
Yeah, thank you. It's not. Equals 0. now we need to find the proper scaling. We will do it with dominant balance. Okay, so we just choose two coefficients and say that they behave the same, and after we find scaling, we need to check if our assumption was correct or not. So let's pick this and this. So we have epsilon divided by delta square. It's asymptotic to delta to the 3/4. So okay, let's write it as delta to the minus 1/4. Okay, so then delta to the 2 minus this is 7. So then for epsilon is 4/7. Okay, I see that. Sometimes it's not. It's tricky. So you cannot guess it, you know. So yeah, let's check it. Let's check it. So we assume that this and this asymptotically behave the same. So epsilon divided by this square is epsilon to the 8/7, or 1/epsilon 1/7. So this and this coefficient goes to infinity, then epsilon goes to 0. And what about this? Delta to 1/4 is epsilon to the 1/7. So this coefficient is negligible with respect to this and this. Therefore, our assumption was correct. Okay. This is the true scale. Okay, so now let's multiply. So let's multiply all of these by epsilon to the power 1/7, and we will have y double prime x tilde plus x tilde 3/4 y prime of x tilde plus x tilde 1/4 times epsilon to the 2/7 y x. Actually, we don't need to write this because that's the only thing for next order correction. But, yeah. Okay, so y double prime x tilde plus x tilde 3/4 y prime of x tilde 0. So we can write it like y double prime x divided by y tilde. Y prime of x tilde is minus x tilde 3/4. Yeah, then I do one integration, right? So
It's logarithm of that.
Yeah.
Derivative.
so it's d1 y prime divided like this. Right? And then we integrate, so okay, this is but we can integrate it, so it's minus x tilde So it will be
7.
7 over 4 times 4 over 7 plus C1. Okay. Then we need to do the exponent, yeah, and integrate one more time. So have y of x tilde is integral is yeah. I think integral of the exponent. Integral of the e to this power minus x tilde 7 over 4 times 4 divided by 7 plus c1 dx tilde. Okay. So now you need to find the C1. Yeah. And yeah, let's write it like this because we have e to the C1 and this integral. And we need to this equals 0 at x equals 0. This. So if we plug in x equals 0, x tilde, I mean, you can I think you can write it as gamma function. If you have your integral from 0 to infinity, and if you change variables, you can finally write it as a gamma function or something. So yeah.
Pick a variable x to the power 7 over 4 and you will get a gamma function.
Yeah, you write t equal this, then you find how this integral looks in the new variable t, right? And let me write the answer. Please just a second. Yeah, you can write this to this satisfy boundary condition. You can write the integral from 0 to x tilde. Here should I write t? So now if x tilde is 0, this is 0. Okay, so no need to integrate this garbage. Okay. So okay, now you know the inner solution. Okay, and you need, for the first step, you need to match inner and outer solution. So this is inner solution. Okay. This is outer solution. Let's match them. For outer solution, it's e squared. For inner solution, we have e to the c1, okay, times this integral. again, this is just some constant. Okay? Some constant. So, and you can write it as a gamma function times something. So, finally for C1, what do you have? So let's write it like this, because this is just some constant. I write it like C1 tilde. So C1 tilde is E squared divided by the value of this integral. So the final uniform approximation is this outer solution, e to the minus 2 square root of x plus 2, plus inner solution, minus matching solution, which is C1. No, it's C1 times E or E squared. So you can write either this or this. Okay, that's the final answer. Do you have any questions?
If our assumption is not correct in the picking the delta, the first term and the final term
So if you
will
pick
behave
this
different.
and this,
will behave different if our assumption is not correct.
if our assumption was not correct, then you plug this delta to this equation, you finally end up with that you have two coefficients that you said that they asymptotically behave the same, and you said that the third one you neglected. So, but if you did wrong assumption, that term, that coefficient that you neglected, it's you will see that you cannot actually neglect it, because it will also blows up to infinity. So for example, if I take this and this, right, what do I have? If I say that epsilon over the delta squared behaves symptotically as this coefficient, so then delta. Now in this case, because you see,
Let's say
It's not the same.
it's not the same.
Plus one quarter. It's minus.
It's yeah, it will be delta to the 9 over 4 or epsilon 4 over 9. Let's try this scaling. So we know that, okay, this coefficient will be like the epsilon to the 1 over 9, okay, and this coefficient will be the same. So, and this will go to 0 as epsilon approaches to 0. But what happened with this one? So delta, it's delta minus 1 over 4, so it's epsilon minus 1 over 9, and this coefficient blows up, which means that our assumption was wrong, that we neglected this. because this coefficient is
the
much
dominant.
larger than this and this.
It's the dominant. If you
Now, yeah, I see that that's dominant, and this is that means that this assumption was wrong, and that's why I need to find a different pair of
And the
coefficients.
third
Match
is
them.
we don't use epsilon in the second and the third term.
What do you mean?
We say that the dominant
the
are
second
the second and
asymptotic
third.
to the third term.
You can say that?
The second asymptotic to third one,
Yes.
Yeah.
What happened then?
but you don't have epsilon here.
Yes.
So it's it doesn't make any
That
sense.
is a question.
No, I mean
There is no epsilon. You
yeah.
can't. You,
We need
you
something
can't
in epsilon.
yeah,
Okay.
yeah, for sure. So that's why you have only two options.
Mhm.
So this and this, or this and this.
Okay.
Because in this case, I have
Delta goes like 1.
yeah. So it's but if delta goes like 1, so it's order of 1, we didn't really rescale our x variable.
Ah,
So
okay.
it's still the same. So that's why the only way how to find the proper scaling is to match something with epsilon with something without epsilon. So yeah, that's the idea.
When I do dominant balance, if the first guess was right, I need to check all the other options.
No, I think in the boundary layer theory there is only one option, but when we did before,
Like in general.
yeah, generally dominant balance may
Have two
may have two options. Yeah. So I mean, if you try one and everything is fine, and you finally found the solution, okay, for the second order equation it should be two solutions, right? And if you in your answer there is only one solution, means that probably you can find other dominant balance that will provide you another solution. That's the main point. Yeah.
Great.
Thanks.
Thank you.
תמשיך ללמוד עליו? תמשיך ללמוד?
חצי שעה משהו כזה.
Hi.
ביי. ואתה? יפה. בסדר? איזה. וואי, אני צריך לעשות את הדברים האלה, אבל אני לא יודע.
תתחיל לך.
מה?
אז תתחיל.
זה פשוט להגיד את
כן, זה נכון.